Okay, I'd like to welcome you to the fourth annual Biard lecture at Caltech. Thank you, Subir. The Biard Colloquium was established by Captain Forrest Biard, showed up here, more affectionately known as Tex. It's named in honor of his parents and has become an annual PMA tradition that features distinguished speakers in physics. So a little bit about Tex. He started his career in the U.S. Navy in the mid-30s, where he worked as a Japanese language officer, and then was assigned to the Japanese code-breaking unit at Pearl Harbor after the attack. After the war, Tex attended graduate school in physics at the University of Maryland as well as at the University of Ohio, during which he also served as operations officer for the first hydrogen bomb test in '52. His interaction with physics teaching came after Navy retirement. He was a physics professor at Long Beach City College, not too far from where we are. Tex crossed paths with Caltech during the year of '61 to '62, when our former president, Lee DeBridge, offered Tex to take classes here for credit in the physics department. And it's said that Tex's interactions with our former Caltech faculty members, Jesse Greenstein and Richard Feynman, led to his passion for physics at Caltech. And he's pledged to remain ever grateful since that interaction. So he and his sister Maddie held true to their promise to Caltech and established a fund to support this lectureship. Okay, so I'm very honored today to welcome our speaker, Subir Sachdev from Harvard. Subir got his PhD from Harvard University, working on frustration order and rapidly cooled metals. He then went to Bell Labs, where he did a 2-year postdoc before joining the faculty at Yale. In 2005, he transitioned from Yale to Harvard, where today he is the Herchel Smith Professor of Physics. Subir's research spans a broad range in condensed matter physics, but it largely focuses on highly entangled quantum phases of matter, and the relationship between highly strong entanglement and sort of properties of many-body electron systems and many-body phases in cold atoms or other synthetically generated many-body systems. He's made numerous contributions to the field of quantum phase transitions. He has a famous book many of you might know, in particular the understanding of quantum phase transitions between ordered magnets and spin liquids. He's also studied the effects of these quantum critical points on the dynamic properties of correlated electron materials like the high temperature cuprate superconductors. And more recently, he's established some remarkable mathematical connections between descriptions of these correlated electron systems and quantum theories of black holes, which he'll tell us about today. So for this work, Subir's been awarded a number of honors, including being inducted into the National Academy of Sciences, the Dirac Medal, and in March of 2018, he'll be awarded the Lars Onsager Prize at the American Physical Society March meeting. So without further ado, let me welcome Subir Sachdev.
Thank you very much, Dave. It's really truly an honor for me to be back at Caltech and also to be delivering the Biard lecture. And so thank you to the Biard family. I really enjoyed meeting many of you today and learning a lot of interesting physics. So as Dave mentioned, my focus is essentially on quantum many-body systems, especially that's found in what we call modern quantum materials. And here we are studying the properties of really infinite numbers of electrons effectively and understanding how they determine their observable properties, their resistivity, their optical reflectivity, and so on. And in fact, this is a field that's, of course, existed for a long time, goes back to the 1930s, and has had a great deal of success. Really, there's whole books written about all the tremendous successes of quantum many-body theory and understanding the properties of numerous materials. And then the hero of this story, of all these successes, is a basic idea of how is it that you can take a theory of 10 to the 23 particles and yet end up with simple equations that describe things in the laboratory. And the hero of the story is the quasiparticle. And roughly the idea is that even though the electrons, say, in a given material interact with each other strongly. When the dust settles, if you're looking at low energy excitations, they behave sort of like particles. And in the simplest case, the quasiparticle is just some electron with some dust around it, some excitations. But if you look at it far enough away, it just looks like a particle with a fixed charge and, say, some effective mass. And then you can use this idea that that's what the low energy excitations are to develop a theory which is not that different from theory of weakly interacting particles, of which, of course, we have a well-developed formalism going back even in classical physics to the work of Maxwell and Boltzmann. So for example, in a metal, the ground state would be, you have some energy levels, and all the states below some energy levels are occupied. That's called the Fermi energy. And the excitations would be simple particle-hole pairs, where you have a particle here with charge plus E and a minus E, and a particle here with charge plus E. And you could just view these as independent particles, largely speaking, which then move through the lattice. And this very simple idea, I mean, it's so prevalent and simple that often if you open a book, you don't even realize that you're making this assumption. You just assume this is true and go ahead and solve. And here's just a very partial list of all the successes of theory of quasiparticles, starting, of course, with what's called the Fermi liquid theory of metals, which was developed in the 60s, where basically the picture I described works. But even in the theory of superconductivity, you have to allow for the pairing of quasiparticles, but still you're thinking about the excitations one lump at a time, effectively. More recently, there's been some very sophisticated theory of what happens in terms of disorder, and again, this works. And even in very low dimensions, there's a quasiparticle picture, but now there's a twist that the actual particle is not the electron. There's some other particle-like excitation. In the case of one-dimensional metal, it's some kind of collective density mode that turns out amazingly to describe essentially all the properties of the system. And even more in the modern topological states, as we call them, like the fractional quantum Hall effect, then there are fractionally charged particles, which are the Laughlin quasiparticles, which are not electrons, but nevertheless are particles. So the low-energy Hilbert space is described by some more exotic particle carrying more exotic charges, but you still have the same description of what's going on. All right, so with all of these successes, then why bother? Maybe this is the idea that's going to work everywhere. But what's happened in the last 20 years, especially in the high-temperature superconductors, there is, so I won't say much more about this rather complicated phase diagram of a material like yttrium barium copper oxide, where I'm showing you all the different phases that appear as a function of temperature and density of electrons in a certain square layer. So this is a high-temperature superconductor. That's all I'll say. But I want to focus on this SM up here, which is above the critical temperature, which is sometimes called the strange metal. And this is exhibit number one of a phase of matter where this ubiquitous idea of condensed matter physics doesn't seem to work at all. I won't go through many of the observations, just a few of them, but really, and it's not for want of trying. There's been many, many theoretical attempts over the last 2 decades trying to use effectively quasiparticle-like pictures, and they totally fail in describing many of the observable properties. So this particular so-called strange metal also now turns out, strangely enough, in these very large class of materials, to be quite ubiquitous. So it's not only present in this material, but other high-temperature superconductors that have been discovered since then, and many other materials which are not even superconductors, but have somehow a new type of interaction, a stronger interaction between the electrons that leads to a breakdown of the very idea of a quasiparticle. So in fact, this metal is sometimes not only called strange, but we seem to not like it very much because we give it rather a pejorative name, like it's bad or it's incoherent. These are technical terms, which mean slightly different things, but these are all the names that have been used in the literature. And among the property I want to focus on in this talk is the fact that its resistance as a function of temperature is a linear function of temperature. Okay, you say, well, there's nothing, what's so strange about that? Well, first of all, so the resistance is increasing as you increase the temperature, which is typically what happens in a metal, which is why we call it a metal. If you take an insulator and heat it up, the resistance goes down, but a metal becomes more resistive as you increase it. But in essentially any quasi-particle theory in the appropriate regime, the resistance should go as the second power of temperature, not a linear power. All right, so that's one problem with the quasi-particle idea. One reason many people suspected already in the early days that there is no quasi-particle description. But more importantly and most strikingly even, the actual value of the resistivity in 2 dimensions now is larger than what you'd call the quantum unit of resistance. So you may have heard about the effect of fractional quantum Hall effect, where the Hall conductivity is E squared over H times a number. So one of the magical things is that this particular combination of fundamental constants, Planck's constant and the charge of the electron, has the unit of resistance. And what we know from the theory of quasiparticles is that if you take a metal and you make it dirty by having lots of scattering, so make it less good a metal, when its resistance becomes of order h over e squared, it'll become an insulator. Basically, the quasiparticles won't be able to move in the disorder because it's so strong and just localize in some potential wells. So here it's clear that that's another reason we believe there can't be a quasiparticle description. So it's very remarkable to find a resistance so large and still metallic, meaning increasing as you increase the temperature. So that's really the essential mystery that's faced us. And so, intellectually this is an interesting mystery, but it's also a practical mystery, because if you want to understand, why is the TC high? That's the one question you always get in studying high temperature superconductivity. Predict TC for me. Well, you're not going to really have a real theory of what's the value of TC unless you understand what's on both sides of it. And on one side of it, universally, is the strange metal. So, and also maybe that's a simpler and easier question to ask, but we've made only limited progress in answering this question. So here okay. This is the state of the field, really, I would say, for a large part of for several years. But I think now, hopefully, by the end of this talk, you won't share all these feelings. All right. So here's another material, the so-called pnictides, or the iron-based superconductors, where again there's a regime of resistivity near the highest critical temperatures of this large resistivity with an increasing linear function of temperature. Okay, so let me step back a bit and try to say a little more carefully, other than showing you these pictures, what do I mean by a quasiparticle? So one definition is the following. You have some complicated many-body system. Say you have a system of n sites, and so just by counting, that system will have the total number of states in the Hilbert space will be exponentially larger than n. It's about e to the n states. Now, it's a hopeless task to describe all of them, but let's say I only wanted to talk about the low energy states. And in the quasiparticle description, that means, as I've already said, that you can talk about the low energy states as just some lump-like excitations interacting with each other. So let those quasiparticle excitations have energy E, little e alpha, and n alpha is a question of whether you have that quasiparticle or not. So it's a binary variable with number 0 or 1. And you can imagine writing the total energy of the system in this form, where you just count the number of particles, and you count pairwise interactions, and so on. And really, the assumption behind all the theories I mentioned in that slide a couple of slides ago is that this kind of expansion is not exact, but quite accurate at very low temperatures. And so what you're effectively doing is describing exponentially large number of many-body states by just a few parameters which are polynomial in the number of sites in the system. So that's really, when you state it this way, it seems somewhat even surprising that you can get away with it, but mostly you can. The other property, which is closely linked to this kind of expression for the total energy, is that once you have quasiparticles, by definition, it means that they live a long time. So if you take a system with quasiparticles, which has quasiparticle excitation, and you kick it a little bit, well, you'll create a bunch of quasiparticles and they'll move around, not knowing about each other. But eventually they will collide with each other. And after a few collisions, you would expect the system to reach thermal equilibrium. So this is the kind of thing, for example, Boltzmann already worked out. How quickly does it take for a classical gas of particles to reach equilibrium through the Boltzmann equation? And you could apply a very similar equation to quantum particles near a Fermi surface. And through a calculation very similar to Boltzmann and using Fermi's golden rule, you find that the equilibration time is of this magnitude. It's basically 1 over temperature squared as temperature goes to 0. So it becomes very long, and that's what you would expect. It goes to infinity, because at very low temperatures, you're creating very, very few quasiparticles, and they just never can find each other. And there's also some effects from Fermi's exclusion principle that makes this longer in a quantum system because of the phase space for final states is smaller. Okay, so I just want you to just remember this. I haven't told you, I've said this is long as t goes to 0, but I haven't told you long compared to what. All right, so that's a quick summary of what's in any textbook in condensed matter physics. So now let's try to find other systems other than the strange metals of the cuprates, which are really too difficult at this point. Are there a simpler system? And that's really all I'm going to talk about. Are there simpler toy models that don't have quasiparticles? So one thing you could try to do is just take a bunch of qubits and which form what's called the transverse field Ising model. So here I've shown an example of a crystal which forms a one-dimensional transverse field model called the cobalt niodate, where each cobalt ion is basically a qubit of some electron spin that can point up or down. And then when these spins interact with each other, and then by applying a transverse field, you get a Hamiltonian of this type. I realized a few minutes ago I should have put a picture of lithium holmium fluoride, because that's the system that our president, Tom Rosenbaum, Tom is even here, I think. Oh, there you are. Sorry. So, Tom, this is really lithium holmium fluoride. Okay. Anyway, so imagine a model like this, where you have these qubits, where sigma z is the operator that just measures whether the qubit is up or down, and sigma x flips it. Am I saying this right? Yeah, there we go. And so this is the interaction between neighboring cobalt ions, this term here, and this is the field that you apply. So there's one dimensionless parameter g, and you can ask, okay, what happens to the system as a function of g? Well, when g is 0, then this is the most important term, and this simply wants the spins to be a ferromagnet, that is, they're either all up or down, and there's two degenerate states. On the other hand, when g is infinity, it wants all the spins to point to the right, where right spin is just this linear combination of up and down. And this is, I call this a paramagnet, and it's a unique state. So just looking and comparing these two, they look so different. There's two states here and one state here. Here you break a symmetry. You have to choose between up or down. Here you don't. And so there must be a quantum phase transition between them. So one idea would be, if you're going to have breakdown of quasiparticles, the place that's going to happen is right near this critical point. Maybe that's a point where there are no quasiparticles. So you could try to solve this theory. And in 1D, in fact, you can solve this model exactly. I won't describe it. And this is the phase diagram as a function of the coupling G and temperature. And what you find for G smaller than GC, that the excitations are these domain walls between up spins and down spins. And each domain wall now behaves like a quasiparticle. So there is a quasiparticle here. And on this side, you have all spins pointing to the right, but you have a few stragglers that still point to the left, or thermally excited, and those left-pointing spins then become quasiparticles. So they're very different, but again, seems like everywhere there are particles, no matter what you do. So you might hope that precisely at GC and in this red region, there are no quasiparticles. Well, it turns out that in this case, that hope is falsely placed. This system is one dimension, and these systems have very special properties, special to 1D, and you can actually rewrite everything in terms of fermions, and then you can see that actually the quasiparticles are present everywhere. And the fermions have this ability to look like a domain wall on one side and a flip spin on the other side. And okay, so this is the model where you might think you find it, but you don't. All right. So then where can you find a system where there are no quasiparticles? I think historically, although it wasn't interpreted in that language when it was discovered, the first place where we actually had a system where we had some reasonable confidence there are no quasiparticles, a theoretical model, is the same model but in 2 dimensions. So you take the same Ising spins but take a 2-dimensional system. And again, you have the ferromagnet and the paramagnet just as I described in 1D. But now the critical point, the original hope that something strange happened at the critical point, does seem to be realized. But the only downside here is nobody can really solve this point. It's a very complicated theory, which in the long wavelength limit we know is related to something called a conformal field theory, which is a very beautiful mathematical structure which was found in models like this by Wilson and Fisher. So that's why we call it the Wilson-Fisher CFT in the 70s. They were mainly thinking about classical transitions as a function of temperature in 3D Ising models. But you can reinterpret what they did as the properties of spins not in 3 spatial dimensions, but as properties of spins in 2 space and 1 time dimension. And in the language of the 2-dimensional quantum system, this turns out to be a system without quasiparticle excitations. Okay, so we know a lot about the Wilson-Fisher CFT3, but it turns out to be surprisingly difficult to say something about dynamical properties, especially at non-zero temperature, of this point without quasiparticles. But one of the things you can argue is certainly true. You can ask the same question I asked about the Fermi liquid. So if I kick a system with quasiparticle, I ask how long does it take to reach equilibration? You can ask the similar question here. How long would the system take? Well, there's various arguments one can make that because of the universal structure of this conformal field theory, that time is just given by this very simple combination of fundamental units, Planck's constant divided by the temperature in units of energy. And the hashtag denotes a number, and that number we know quite definitely is a universal number. That is, doesn't depend on any details. You could take a triangular lattice or other lattices. As long as it's translation invariant, it'll be the same number. It's going to be independent of all coupling constants. So it has this rather remarkable property that things are independent of the microscopic details, and the time scale is just determined by absolute temperature. But you can ask the second question of what is the value of this hashtag? What is that number? You said it's universal. What is it? Well, unfortunately, we don't really know even today. It's very hard to compute in any systematic way. And even numerical techniques don't work because you have to solve a strongly interacting system in real time at finite temperature. And that's maybe a quantum computer will someday tell us what that number is, but we don't know what it is with any accuracy. We have some estimates, but they're very poor estimates as far as we can tell. It'd be great to have experiments, and I'm hoping that there will be experiments in 2 dimensions that, for example, can fit that number. All right. So this is a nice model, and I've spent many years thinking about models like this, but it's still very hard to work with. So can we find something even simpler? And it turns out there is something much simpler, and that's what I'm going to spend most of the rest of this talk about. So to set that up, let me talk about a very simple model with quasiparticles. Okay. So here's the toy model. So this is just something that just solving simply for the sake of solving because it's solvable. Yes?
In your 2D system, do you not find quasiparticles because there's a boundary where it's asymmetric?
No, there's nothing related to that. It's related to the fact that it's really a strongly interacting conformal field. I mean, it's a scale invariant theory at long scales, but you flow to a point where any kind of basis you use of quasiparticles, they interact very strongly with each other. You can't separate them. Okay. So we take imagine a bunch of sites, and let's put a few electrons on them, about half of them. And I take a very simple model. I just allow the electrons to hop randomly from any side to the other. So there's some tunneling matrix element for, say, an electron to do that, and so on. So these are all allowed processes, and each of them has some amplitude. What amplitude? Well, it's some random number. Just pick a random number for every one of them, and there it is. So these are just free electrons hopping randomly. If you want to see some equations, this is how you write it down. This is the operator that takes the electron from side j to side I. Tij is some random number with zero mean, and there it is. So this is just individual particles hopping, and it's clear how we solve this. You just diagonalize this Tij. So Tij is just a random number, so you're just diagonalizing if you have n sites, an n by n matrix. So we know a lot about, that's a problem, a lot is known about the structure of random matrices, and you can just use some of the information to say much more about the properties of the system. So in particular, the density of states of these eigenvalues form the famous semicircular form, and here's some Fermi energy, and you occupy all the states in here. And the energy eigenvalues epsilon alpha are roughly equally spaced with a spacing of order 1 over n, where n is the size of the matrix. Okay. Now I want to focus on not the individual eigenvalues of the random matrix, but the many-body eigenvalues of the many-body system. Well, that's very simple. In this case, this expansion I wrote down truncates even already at first order because these are free electrons. Sorry for belaboring this very simple problem. So the EA or the E alpha are the eigenvalues of the Tij, and Na is 0 or 1, and this is the total energy. So by definition, this is a system with quasiparticles. Now what I've done here is plotted all the eigenvalues for capital E for a system of 12 sites. So I just took a random 12 by 12 matrix, determined its 12 eigenvalues, and then from that I constructed 2 to the 12 energies, because n alpha can be 0 or 1. So that's 4,096 energies, and this is the value of all of those 4,096 of them. So I just want to focus on a few important properties here. First of all, the width of this is of order n, and the total number of states is 2 to the n, so the mean spacing has to be 2 to the minus n. So they're very closely placed. Whereas the spacing between the E alpha is 1 over n. So what this means is that I go from one level to the next, the n alpha changed completely. So the set of occupied particles changes completely, and just by accident I can find some level which is really, really close to it. That must be how it's all working. However, there's something very interesting. What about if I look at the lower levels? If I look at the lower levels, then what's happening is I'm occupying all these single particle levels below the Fermi energy, and their spacing is 1 over n. If I want to create a low energy excitation, I don't have any choice. What I have to do is take the topmost level that's occupied and move it to the lowest level that's empty. And that will cost me an energy 1 over n. So therefore, I find that down here, the energy level spacing is actually much larger than anywhere in the middle of the spectrum. That's just a very simple feature of this model coming from this very simple equation. Okay, so that's very simple. This is a model with quasiparticles. So now let's destroy them. So the way we're going to destroy them, again, take these n sites and occupy half of them. And I'm going to allow these electrons to move, but only going to allow them to move in pairs. That's the key thing. So this is, as I said, it's called this SYK model. Okay, I'm going to call it that. And so the processes now are pairwise motion of electrons. So pick any pair and move them anywhere you want. And so there's roughly n to the 4 choices for these moves. And this is now really in the many-body space. So now it's a many-body Hamiltonian. And the matrix that you're using to describe the system is not n by n. It's 2 to the n by 2 to the n. It's a much, much bigger matrix. But the number of random elements is only of order n to the 4th. And all of these are random numbers. And that's it. That turns out, amazingly, to be the simplest model, which is known to not have quasi-particle excitations. And hopefully I'll convince you by the end of this talk, well, there are indications that it's actually a good starting point for even thinking about realistic strange metals. And it also has connections to black holes, and hopefully I'll finish and have time to describe that. But that is the model. That's it. There's nothing else you need to know. You could present this to a mathematician, and one would hope that they would come back to the solution in a few years. Well, maybe it is tricky to solve, but the physicist's point of view actually turns out to be quite useful, I think. So that's it. This is the three equations that fully define the model to a mathematician. You have these fermion operators that anti-commute, and pairs of fermions can hop from site KL to site IJ, and these uij KL are all random numbers. So some variant of this model was proposed almost 25 years ago by my first student, Jinwoo Ye, and myself, and Alexei came up with a model very closely related to this one. Alexei's improvement has allowed many new ideas to come to the field, including more practically allowed numerical diagonalization and tests of these ideas that wasn't possible in the form that we had proposed it with reasonable computer speed. I should also mention a model like this has a long history in nuclear physics. It's called the two-body random ensemble. I was told that after giving a talk like this somewhere. But the model was written down, but really not much was done. The large N limit was not taken. Its properties were none of the properties I'm going to describe were understood. But it was abandoned, but it was looked at for a while, numerically. Okay, so now let me just do exactly what I did for the simple model with one particle hopping, and just redo that for the two particle hopping case. So as I mentioned, now it's a much harder problem. I have to diagonalize a 2 to the 12 by 2 to the 12 matrix. Fortunately, that can be done, but I very quickly run out of steam. If you put n equals 40, you can't diagonalize 2 by 2 to the 40 by 2 to the 40, at least the computers I have access to. There are some really powerful computers that can do 40. On the other hand, the previous problem with 40 sites, you just have to diagonalize 40 by 40 matrix, which is totally trivial, of course. So this very quickly becomes intractable as n grows. So what do you find? So here again, I've shown you the energy levels for 2 to the 12 energy levels. And again, you would expect anywhere in the middle of the spectrum, the spacing is 2 to the minus n. And the picture doesn't show it well. I mean, I could have shown you the picture for 2 to the 20 states, but you wouldn't be able to see anything on a slide like this. It would just be one uniform sheet of black. But anyway, so it turns out that the energy level spacing at the bottom of the spectrum is also much larger than in the middle, but it's not that large that it was for quasiparticle. It's not of order 1 over n. It's still exponentially small, but this coefficient S0, which we worked out a while back, is this transcendental number. All you need to know about it is smaller than log 2. So this spacing, as n goes to infinity, is still much larger than the spacing over here. So there seems to be a lot of states at very low energy, exponentially large number of them, not just a power law number of them. And this pretty much means that you couldn't possibly describe all these states in some expansion of this type. So that's one of the indications that there are no quasiparticles in this very simple system of pairwise hopping. All right, so now lots been learned. In the 25 years, people have been looking at this problem off and on. And I've just summarized some of the things, not in any particular historical order. So because of this energy level spacing being so small, the density of many particle states is exponentially large. It's e to the n S0. More recently, people have figured out the first correction to that, the cinch factor. And this came from a variety of sources, some involving more precise analysis of the SYK model, but others coming really from quantum gravity, amazingly. And I'll say a bit more about that in the latter part of my talk. But again, this has been tested numerically on a model like this, and it seems to work very well. Because of this exponentially large density of states, the entropy as a function of temperature is not zero as temperature goes to 0. So in fact, we discovered this in 2001, and it's partly and we put this result in an appendix because we're kind of embarrassed by this. You're violating the third law of thermodynamics. How can this be of any use to anybody? Luckily, we did put the result in there because it turns out this is really not a bug, but actually a very useful and interesting feature of this model, and really quite generic to models without quasiparticles, without a spatial structure. These were not things that were clear to us in 2001. More recently, people have computed the correction to this. It goes linear in temperature, and this number gamma is the same as the number gamma over there. You can also look at Green's function, a correlation function as a function of time. This is the first thing we did, and it decays with 1 over square root of time, and that already was an indication clear to us that it should, it's a system without quasiparticles, because a system with quasiparticle would have a 1 over tau. Okay, that's a technical point I won't spend much time on. Then my friends and collaborators in Paris, Antoine George and Olivier Parcolet, figured out how to solve this model at finite temperature. And they noticed they had this very simple form at non-zero temperature. And it's a sign of something, and that sign is the combination of the time and the absolute temperature in units of inverse time using Planck's constant. So notice there's the U or the various couplings don't appear anywhere in here. Now this particular form, was a surprise when it was obtained, but it immediately, said that something very unusual and remarkable was going on, because this is, some of you may realize who've studied conformal field theory, that this is typically the form that you get in systems that have conformal invariance, similar in low dimensions. And the conformal invariance is related very much to the conformal invariance I mentioned for the Wilson-Fisher fixed point in higher dimensions. Anyway, so from this form, and more recently in some explicit studies, we can ask the question, how long would the system take to equilibrate if you kicked it? And again, the time is just a combination where this, say, reaches about a 1. It's again this time h bar over kt, which we had discussed earlier should be present in the Ising model. All right. So now I've given you two systems which have no quasiparticles. And so what have we learned from those systems? So first of all, we've learned that this kind of expansion of many body states in terms of some single particle energy level doesn't work. So that's great. That's sort of defining a system by what it's not, but it's a start. It's not, doesn't have quasiparticle. If it doesn't have quasiparticle, what good is it, and what does it really do? So the two examples of the system we've looked at, it seems that they seem to equilibrate in this basic time, h bar over kt times some number. That seems to be some of the natural time scale for systems that has essentially infinitely strong interactions, so that a particle-like description fails. So one thing you notice about this number is as temperature goes to 0, this number is much shorter than the Fermi liquid time, which was h bar over temperature squared. Where did it go? There, 1 over temperature squared. So you might expect that maybe this number is a lower bound, that really the essence of a system without quasiparticles, that it reaches thermal equilibrium and some chaotic state as fast as possible. And so you might say, well, there is some kind of universal lower bound in all systems where this equilibration time is always bigger than this time, with some number c of order 1. We don't know what that number c is. It depends, I guess it would depend precisely how you define tau equilibration, but anyway. And this kind of lower bound, one can see, actually is obeyed by everything we know about all the systems that have been studied. So for example, in a Fermi liquid, it certainly obeys this bound. And this bound is not an empty statement, even though we don't know the value of c. For example, there can be no system where the equilibration time goes as 1 over square root of temperature as temperature goes to 0. This could happen just by scaling invariance. You could imagine such a system, but it never does. No one's ever found such a system with an equilibration time that is as short as that. It's always longer than h bar over temperature. Another interesting thing to notice about this lower bound is it's very much a quantum thing. It's got h bar on the right-hand side. So if h bar goes to 0, then this time there is no lower bound. Tau equilibration greater than 0, obviously. And that's true. In classical systems, I have a bunch of springs, nonlinear springs, and I kick them. They will equilibrate in general. Well, I can just scale up all the spring constant by 5, and they'll equilibrate 5 times faster. There's nothing prohibiting how quickly any system thermalizes. You can put any energy scale you want. But in quantum systems, that doesn't happen. And the reason it doesn't happen is that if you scale up some coupling constant, what that does is that it becomes so strong that it prefers some very conventional state, like a ferromagnet, like I showed you. I made G infinity, it became a ferromagnet every point to the right. And then if I want to perturb it, it costs a lot of energy, because you have this very large coupling constant. So you develop gaps, so you develop some regular order, which has quasiparticles, which then become very rare because the quantum gap makes them very expensive. So you really have to find systems that equilibrate faster quantum mechanically. It doesn't pay to just scale up some coupling constant. You have to be at the regime where there would be no quasiparticle, and that seems to only happen at these very special points. And then you're just determined by this universal time scale, h bar over kT. Okay. So, how am I doing on time, Dave? I have to end at 5, is that right?
Just a few minutes past that.
At 5?
Yeah, 5.
Okay. So now I want to talk about some recent work, and there's a lot of work on this very much ongoing. I'm going to show you a very nice paper by Leon Valens and collaborators at Santa Barbara, where they're trying to take this model, this very, which really was a toy model for us for a while, and make it a little more realistic as a model of a strange metal. So here's the model. So that every circle here is the model I've described so far. So now I think of these sites in the circle as some orbital labels in some big atom. So I have some big atom here which has lots of orbitals, and these sites are the orbitals that can be occupied by some electron. And depending on the orbital occupation, so I, J, K, L are now orbital labels. You have some random repulsive energy, Ui, J, K is a random number, which is not repulsive, it's a zero mean. So that's a bit artificial, but we can see how to get rid of the average interaction. And now you allow for the electrons to hop from site to site. That's the blue line, between different atoms, again with the random numbers. Now, one can make this a lot more realistic, but this is the simplest model that's solvable. And many of the more realistic models are very much understudy, and I don't have pictures to show you, but just take my word, you get very similar results. So what happens? So now here's a model where you've got space. And what's happening, roughly speaking, that on each atom already, the electrons are losing their identity. So they're becoming incoherent. And somehow these incoherent objects have to hop. So there's no particle left to move. It's a little more difficult for them to hop from site to site. But still they do hop, and you can ask, is it a metal? What are its properties? So through an exact solution of a very simple model like this, Leon et al. Have in fact obtained this strange bad metal that I talked about. So in particular, they find that there's some coherence scale, which is about a t squared over u. T and u are the two energy scales here of the interorbital interaction and the hopping between sites. So there's a relatively low energy scale, which you can make as low as you want by making u large. And below this energy, quasiparticles emerge. So if you look at the resistivity, for example, it goes as t squared, and that's something shown in this graph here. On the other hand, at energies above this coherence scale, you get the physics of the SYK impurities. Each atom behaves like an SYK dot with this 1 over square root of time power law decay. And when you then do a simple, essentially a second order perturbation theory estimate of how easily current propagates through the system, you get a resistance which is of this magnitude. It's the quantum unit of resistance in 2 dimensions. This will work in any dimensions. You'll get the appropriate quantum unit of resistance up here, h over a squared. times the ratio of temperature to this energy scale, which by definition, since T is bigger than EC, is much bigger than 1. So you've got really the two crucial criteria you want in a strange metal. First of all, the resistance is increasing as you increase the temperature. It's increasing a linear function of temperature, and it's much larger than h over e squared. So it's strange, well, because it's a linear function of temperature. It's incoherent because it's coming from incoherent hopping. And it's bad because the resistance is so large. Okay. So that's quite remarkable that this very simple model all of a sudden seems to be just what we've been looking for all these years. Okay, that's the low temperature behavior I mentioned. All right, so I have about 10 minutes, Dave. So now I can go to the second part of my talk, or at least mention what does this have to do with black holes? Why should it have anything to do with black holes? Not, I've been a dyed-in-the-wool condensed matter physicist through the entire talk so far. Here I've shamelessly shown some pictures from LIGO, so forgive me about that. So what do we need to know about black holes? Well, there are two crucial properties of black holes, going back to work of Bekenstein and Hawking. A black hole always has a temperature called the Hawking temperature, associated with quantum fluctuations near the horizon of a black hole. And furthermore, the entropy is proportional to the surface area. But the real crucial property for this discussion is the question of what happens when two of these black holes merge. So here again I show the famous LIGO picture. I hasten to add that quantum effects have nothing to do with this, as you well know, I'm sure. But I just want to focus on the very last stage of this black hole becoming a perfect featureless sphere. So this is something that can be described by Einstein's equations, and that's called the ring down time, and that turns out to be of this magnitude, and for the original LIGO black hole, that's about 8 milliseconds. So that's nothing to do with anything that's observed, but the very last stage of the perfect sphere. Now, on the other hand, I can think about the same black hole in a quantum language. So that black hole, Hawking taught us, actually has a temperature. And what is that temperature? Well, it turns out that temperature is basically related to the ring down time by this very simple equation. It's just the ring down time is related to the Hawking temperature as the time is h bar over kT. So I find again, if I think of the black hole as a system in equilibrium, a black hole turns out to be a system which equilibrates, again in precisely the same time that I found for a system without quasiparticles. And that's really not an accident, and that's really a deep connection between systems without quasiparticles and black holes. They both share this ability to reach thermal equilibrium in really the fastest possible time that we know any quantum system does. So if you interpret it in this scale set by the Hawking temperature, it's again h bar over kBTH. So that's the basic connection. So I'm just going to run through a lot of history about connections between quantum gravity and quantum systems without gravity, the whole subject of holography. And this, of course, goes back to the famous ADS-CFT correspondence, where a particular conformal field theory, you can view this as some highly supersymmetric version of the Wilson-Fisher theory in 2 + 1 dimension. So there's a maximally supersymmetric conformal field theory in 2 + 1 dimension, was shown by Maldacena and collaborators to be equivalent or dual to a conformal field, to a theory of quantum gravity in 3 dimensions in anti-de Sitter space. So anti-de Sitter space has this particular metric. Okay, so what does this buy you? Well, this immediately actually helps us understand the 3 things I mentioned about black holes, if you believe this correspondence. And there's a huge amount of evidence from string theory that this correspondence holds. So it turns out that this anti-de Sitter space metric can be generalized to finite temperature. That's really what happens to this conformal field theory at 0 temperature. So if I heat up this conformal field theory sitting on this 2 space dimensions here, then I know I'm rushing through this. The bulk turns out to have a horizon at a distance r from the boundary. and this distance r is related to the temperature. So in the previous slide, when the temperature was 0, r was infinity. So you get a black hole with a horizon, which extends infinitely in this 2 spatial dimensions here, corresponding to the infinite extension over here. So Maldacena et al. Tell us that this conformal field theory finite temperature is equivalent to the theory of quantum gravity with this black hole. Well, this immediately helps us understand this time of h bar over kt. Because if I kick this conformal field theory and ask how long does it take to equilibrate, well, from everything I've said, that's h bar over kt. On the other hand, if I take the theory of gravity and I perturb the black hole, well, how long does it take to equilibrate? Well, Einstein's equation tells us is also h bar over kt. Secondly, we can also understand the area law. So Hawking tells us that the area of any theory of quantum gravity with a black hole is proportional to the area of this black hole horizon, not the volume of the black hole. Well, that's perfect, because if this theory is equivalent to this theory must also have an entropy proportional to this area. Well, that makes perfect sense. It's a 2-dimensional theory, so it must have entropy going at its area. So again, you understand the dimensional reduction, why a quantum gravity theory in 4 dimensions is equivalent, 3 space and 1 time dimensions, is equivalent to a theory of ordinary theory like this conformal field theory of supersymmetric Yang-Mills in a lower number of dimensions. Okay. All right, so now you can ask the question, here's my SYK model, is it dual to some black hole? And now, that's not a totally crazy question to ask, because we've already seen that the SYK model has this equilibration time of h bar over kt. So perhaps there is some black hole which is dual to it. So what I'm going to do here is put this model on a finite torus, because really I'm going to give it some spatial extent, because gravity requires a little bit of space to work in. But it's a finite gravity. So it's, again, let's say 2-dimensional space. This is a 2-dimensional torus. And ask, is there some black hole which is similar in properties to what we know about the SYK model? And so these are the list of properties I gave you a while back. I'm just going to erase a few that were not known a few years ago. And it turns out that all of these properties that are written down here are, in fact, matches a particular black hole. And it's this black hole. It's the black hole not of just Einstein gravity, of just an ordinary neutral black hole in anti-de Sitter space. It's a charged black hole in anti-de Sitter space. So there's some technical differences between charged black holes and neutral black holes. So the way to think about this is, in the theory of quantum gravity, there's a boundary and you've smeared some charge density on the boundary, and this creates an electric field which then obeys the Einstein-Maxwell equations in the 4-dimensional bulk. And so you get what's called a Reisner-Nordstrom ADS black hole with a horizon. And right near, if you go very close to the horizon has a very different form from the ADS Schwarzschild black hole I'd shown you earlier. It has this particular form. It factorizes into a space-time which is 1 space and 1 time, the ADS2, and a torus which is similar to this torus out here. So effectively, if you're looking at very low temperatures where the torus is shrunk to a point, what you find then is that this SYK model, his properties match perfectly to the properties that you would deduce from holographically working out the properties of this particular theory of gravity in some semi-classical limit. So now this correspondence has been studied a great deal, and the very simple matching arguments have been made now much more precise, and I don't really have any time to go into that. So not only these properties, but also the ones I raised, especially through some brilliant insights of Alexei, all seem to work out, at least the properties are listed here, between the boundary SYK theory and the black hole. Okay, I think I'm now out of time. I had a few slides here, just a couple of slides about connections to quantum chaos, because this is a language that many people have been using recently to discuss this physics. So just very briefly mention it. There's some people have, especially Schenker and Stanford, introduced the concept of a Lyapunov time, which is known to obey a bound with very similar to the bound discussed earlier with the prefactor known, and the SYK model and gravity saturate this bound much more precisely here with the factor of 2 pi than the more qualitative considerations I had mentioned earlier. So let me just stop. So now I can summarize what do I mean by quantum matter without quasiparticles. Well, these are the two basic characteristics. One is that the many-body energy levels do not have a decomposition between small numbers of quasiparticle excitations at low energies. And secondly, these are systems that thermalize or reach many-body chaos in the very shortest possible time, which is of order h bar over kt. And these basic properties, these central properties of quantum matter without quasiparticles, they share with black holes. So thank you.
Questions? You guys start with one.
Sure.
So in the numerics on the 2D Ising model,
Yes.
I mean, how do they compare? You said the numbers are not very trustable, but how do they compare to 1 over 2 pi?
Well, I don't remember. They're probably of the same order, I suspect. Actually, I don't think anyone's really done the 2D Ising. I have a paper where I did some epsilon expansion a while back, long before the 2 pi was being talked about, so I actually have never compared it. But there is a paper where I had a not very believable epsilon expansion. I mean, the difficulty is really this whole issue of analytic continuation and working in real time. If you want, some critical exponent or operator product coefficient of the conformal field theory or things like that, you can work that out. But once you go to this kind of dissipative real-time process, it's not so easy.
Jeff?
Sorry? Yes. In this particular model, yes. In fact, the model that I showed you, sorry.
And what are the topological properties of the model?
Totally trivial. And the topological in the sense of band structure, no, we're not.
In the sense of popping around the loops and getting complex phases.
Oh yeah, so that's something we're very much working on because that's important for the magnetoresistance and the Hall effect. I would say that those are not explained yet. There are certain striking properties of strange metals in the magnetic field that are also quite universal. I think my student Avishkar Patel is actually quite close to a theory of that, but let's see. But that's very much, I think if that also works, then we'll be closer to declaring victory. But yeah, that's a crucial thing that needs to be understood. Yeah. Yeah. I suspect the boundary system should also have to be rotating. Yeah, so that's really not very much studied as well. Yeah, I mean, I guess the original Strominger-Waffa is something like that. They have some angular momentum. But their conformal field theory also has got some angular momentum in it. Yeah. But I haven't studied that very much. Yeah.
Is there any conceivable way that, say, in a high-DC superconductor phase diagram, this model or something similar to pop up as an effective theory?
No. I think, no, I mean, the number of orbitals on each atom in high TC is 1, not infinity. But, that shouldn't scare us. In the famous Wilson-Fisher epsilon expansion, they worked out the theory in 3.99 dimension, as they famously said. But when you put epsilon equals 1, it's actually pretty good. So here, I think there is preliminary evidence from various numerical studies that even though this model is only exact at n equals infinity, even at n equals 1, it actually seems to do a pretty reasonable job. But we don't fully understand why. This is all very much work in progress, but that's, yes. Yeah.
So from the quasi-particle view of black holes, how
Yeah.
do you explain black hole evaporation?
Well, black hole evaporation, no, that's a good question. I have no idea. So that's actually one of the reasons it's important that this particular black hole is an anti-de Sitter space. So unlike flat space, where the space is asymptotically, it's not curved as it is anti-de Sitter, these black holes are in equilibrium. They don't evaporate. They're eternal black holes.
They don't evaporate?
No, they can be sure. They don't evaporate in it, yeah. So these are in thermal equilibrium. So you can kick them around a little bit, and then they'll come back to some equilibrium, perhaps at a different temperature, but then they just stay there. So time-dependent evaporating black holes, I think, is a much, much harder problem. I am not qualified to say anything, and I know many string theorists are thinking about it.
Any other questions? Okay, thanks, Subir, again. If you go to n equals 1, then you don't have then you don't have pairwise hopping. How does that work?
No, the hopping between is yeah, I know. So within orbital, you don't have that term, but you still have a U-term. Thank you very much. Yeah. So what you can, there's a way to say it more carefully is that when you take the large unlimited, you get a certain set of graphs. And so you just take the same Feynman graphs and just solve them by putting n equals 1 everywhere. That's what you do. So it's just a certain graphical expansion that you're solving self-consistently, and you may as well do it for the ordinary Hubbard model, but there's no reason to say the corrections can be ignored. But I think we have some hunches of why the corrections are small. Yeah, but that's very much work in progress. Yeah.
I'll let you go, except to say I think Nai-Chan has you next. So
Oh, yeah.
She'll bring you in.
Okay, all right, thanks a lot, Dave.
Okay, I'll meet you from around.
Okay. Hi.